Welcome to the presentation of our paper titled Packet Header Attack by Hardware Trojan in NOC based TCMP and its Impact Analysis. This is the flow of our presentation, starting with the introduction to TCMPs and NOC, followed by Hardware Trojan, Threat Model, Experimental Setup, Detailed HT Impact Analysis, and ending with Conclusion and Future Works. Tiled chip multi-core processor is a class of system on chips that integrate multiple cores on a single tile. These tiles are interconnected via packet-based network known as network on chip or NOC. Due to the tighter time to market constraints and the need of reduced design cost, manufacturers have started exploring the possibilities of integrating several third-party IPs to design TCMP that brings security vulnerability into the design. This figure represents the architecture of 4x4 mesh 16 tile TCMP, where each processing element is represented by a purple numbered square connected to routers, and routers in turn connected to a network to communicate with each other. Each router is further having multiple components including routing unit, VC allocator unit, switch allocator unit, and a crossbar. Packets in NOC are split into smaller units called flits. There are three types of flits: head flit, body flit, and tail flit. Head flit contains all the essential information known as control fields that is helpful to travel a flit from source to destination. Body and tail flit contains data payload. Hardware Trojan is a malicious circuit inserted in an IC that can alter system behaviors to produce undesirable consequences. For the normal and genuine scenario, inputs is given to the circuit and genuine output is produced. However, if HT or malicious circuit is involved, upon triggering that HT, an altered output is produced. This work is intended to showcase one of such kind of the cases where the HT alters one of the control field of the head flit. There are works in the literature that talks about the possibilities of having HT at various components of NOCs, including routing unit, input buffers, VC allocator, switch allocator, or it could be a crossbar. In this work, we assume that HT is present at one of the input buffer of VCs that modifies the DID to a random DID without violating XY routing. For the detailed analysis, our HT restrict to modify only L1 miss request packets. When DID gets changed, HT received at wrong destination, and that leads to a packet dropping. Let me walk you through with an example to understand the threat model. Here 4 is considered as source tile, 15 is considered as destination tile, and this is the green path that should be followed in order to reach a packet from 4 to 15. When a genuine packet starts traveling, gets through the HT infected node, that is 5 in this example, and it changes the destination ID to a random node 3. So, instead of 15, now the packet would reach to 3, and upon reaching 3, after the verification, 3 drops the packet at wrong destination. This is the experimental setup used for collecting the results. Out of order CPU alpha architecture processor is used. MSHR capacity is 256 entries per core. ROB capacity is 192 entries per core. L1 and L2 cache is 16 KB and 2 MB respectively, while main memory is 8 GB. Ruby memory model and Messy protocol is used, and for NOC modeling we use Garnet 2.0. We modeled 4x4 2D mesh topologies while using XY algorithm for routing. HT attack probability is taken as 0.1, and in order to build the simulation system, 1 million instructions are fast forwarded while another 500,000 instructions are executed for detailed simulation. We work on the 4 architectures for evaluation. First is NHT, where no HT is present. We call it baseline architecture. HT is the architecture where HT is present at router 5. HTR1 and HTR2 is the case where retransmission is considered for 1000 clock cycle and 200 clock cycle respectively. These are the 5 workloads that is used to collect the statistics. SPEC 2006 benchmarks are used for experimentation. A WL1 considered all the high MPKI benchmarks running on all the cores. WL2 represents when all the low MPKI benchmarks are running at all the cores. WL3 represents the 50-50 combination of it, while WL4 and WL5 represent 75% high and 25% low and vice versa. The impact of HT is analyzed using the TCMP matrix: impact on core, impact on cache, impact on NOC by varying Trojan probabilities. Here the HT impact analysis at core level can be seen with the help of comparison of final ROB update time. The first graph shows core number at x-axis while y-axis represents final ROB update in execution window. ROB is an in-order commit where the instruction can get issued in out of order and can also be completed out of order but will be committed only in order. So we can see here at core 0, core 1 and all other core except 5, 11 and 12, we can see that ROB gets full at very early stage and hence they stalled the core. 5 is an HT router, that's why the impact of stalling is not visible here. 11 and 12 are considered to be that core where the packets of these cores have not travelled from HT core. In case of the IPC, we can see if ROB buffer gets full early, then lesser number of instruction could able to complete within the simulation time. And we can see the cores running low MPKI benchmarks shows high IPC, while core running high MPKI benchmarks show lower IPCs. IPC's value dipped significantly except in core 5 and non-impacted cores 11 and 12 when HT is active. Now we talk about the HT impact on cache. Here we try to observe the average miss penalty and number of L1 misses. Number of L1 misses is given by the right y-axis, while the left y-axis represent average miss penalty. This solid graph represents all the cases where average miss penalty is taken, and all the dotted graph represents the L1 misses. Here we can say HT's impact is visible by reduced number of L1 misses in impacted core, because lesser number of instructions get executed and those who executed get stalled as ROB entry becomes full. Average miss penalty for L1 cache is the number of cycles needed to fetch the required data block into the L1 cache from L2 or main memory. Average miss penalty rises for the retransmission cases compared to baseline. Now we try to emphasize on what is the HT impact analysis for core and cache across all the workloads. We can see the severe degradation in the IPCs due to the HT cross. All the cores can be seen that there are significant IPC degradation across all the workloads. No impact on core 5 is registered anywhere because core 5 is the router where HT resides. Impact on average miss penalty and number of L1 misses for different workloads is also similar across all the workloads. L1 misses falls as more cores comes to halt. We can see a rise in average miss penalty for retransmission enabled architectures. Now we talk about HT impact analysis at NOC level. In this table, we show the number of NOC packets where A is total packet generated in NOC, B represents L1 request packets passing through HT infected router, and C represent total packets modified by HT router. Here we can see for all the workloads, the number of packets that is generated in NOC is dropped significantly, because very soon the core gets stalled, that eventually leads to less number of packet generation. However, the average packet latency is not impacted much by HT, and in this example we have taken the workload WL3. We also have analyzed and tried to capture the HT impact by varying the Trojan probabilities, and here we can see while we increasing the HT probabilities, IPC is further getting reduced. In some cases, for P is equal to 0.15, we can see the number of retransmitted packets again got lesser IP because number of retransmitted packets are impacted again by HT. And retransmission efficiency is limited to the Trojan attack probability. So, I would like to conclude by proposing the packet header attack by hardware Trojan in NOC. We have shown the qualitative and quantitative analysis of the impact of HT at core, cache and NOC level. The proposed retransmission technique seems ineffective due to the high overload. However, lightweight cryptographic and authentication techniques can be explored further. The future work revolves around building a cost-effective HT mitigation technique against this HT.